In this section, we are moving into object-oriented programming, or OOP, which is a way of structuring code around real-world entities. Instead of thinking only in terms of separate variables and functions, we start thinking in terms of objects that have both data and behavior. This is a very important shift for you because it will help you model real systems more naturally and organize larger programs more clearly. By the end of this section, you should understand what classes and objects are, how to create and use classes, how encapsulation works, and how to build simple systems using objects. So you will also have some multiple objects, which is important because you need to understand early that one class can be used to create many separate instances. So why OOP? As programs become more complex, we need better ways to organize them and make them scalable. If everything is just scattered and variables and disconnected functions, the system becomes difficult to manage. OOP is one solution because it groups related data and behavior together into meaningful units. A car can be treated as an object, a student can be treated as an object, and a building can be treated as an object. Each real entity has attributes which describe its state and behavior. So this is exactly the mindset OOP encourages. OOP is about representing real-world things in code so that software structure matches system structure more naturally. That is why it is so important and useful in domains like engineering, as well as monitoring, simulation, where the code often needs to reflect how the real system is organized. What happens without OOP? One function may depend on global data, another function may modify it elsewhere, and as the system grows, it becomes harder to trace what belongs to what. This is exactly the kind of complexity that OOP tries to reduce. With OOP, data and behavior are bundled together inside an object. That means, instead of having information in one place and logic in another, the related pieces are grouped into one container. This makes the program easier to reason about because each object represents one coherent thing. So here is a bit of vocabulary of OOP. A class is the blueprint. An object is an instance of that blueprint. An attribute is data stored in that object. And a method is a function that defines behavior. So these four terms form the core language of this topic, so you should become very comfortable with them. Now let's look at the example student. So here, the class represents a learner, the student class. The attributes are things like name and grade, and the methods represent behavior such as studying. You can see that a class is not abstract for its own sake. It is structured representation of something more meaningful. Think in things, not just variables. Instead of only asking what variables we need, we start asking what things exist in the system. Once we identify the things, we can decide what data they hold and what behaviors belong to them. What is a class? A class is defined here as a blueprint or template for creating objects. The blueprint metaphor is actually very useful. A class is not yet the real thing. It is the plan that tells Python what structure and behavior an object of that type should have. Just like a house plan is not an actual house. A class definition is not yet the object. How do we define a class? Class student with the colon followed by pass. The use of pass is important because it lets us define an empty class when we have not added details yet. This is a good first syntax example for you because it shows the form of a class without too much complexity. Now let's move to object. An object is explained here as an instance of a class meaning a real usable entity created from the blueprint. The class gives the design, and the object is the actual thing we work with in that program. This is a distinction that you need to be clear about. So how do we create an object? Here we are creating an object with s1 equals, then we are calling the class student, and then printing the object. So here we are just calling the class name like a function creates the instance. At this point, the student class is just being inside this object. You can see that classes are used to generate actual program entities. The output shown here is Python's default project representation, something like the main, then the student object. It shows that the object really exists even though it does not yet have custom display formatting. The important concept is not the exact printed form, but the fact that a student instance has been created successfully. Now we are moving to constructor. Constructor init as the method used to initialize an object when it is created. It is automatically called upon creation and is used to set starting attribute values. This is how we make sure a new object begins with the right internal state. Here you can see a student class with an init method that takes self and name, then sets the self.name equals name. This is the first real example for you here of attaching data to an object. The important lesson here is that the constructor receives the incoming data and stores it inside the object. Now we are creating a student object with Ali, and then we are printing s.name. The key point is that the object is no longer empty. It now contains specific data, and that data can be accessed through the object reference using dot notation. The output is simply Ali, confirming that value passed into the constructor was stored correctly in the object's name attribute. This is a very important moment in the lesson because it shows you that objects can hold and expose specific data. The self refers to the current instance. This is one of the most important OOP concepts. It allows methods to work with the attributes of the specific object that is calling them. Without understanding self, students would usually struggle with methods and constructors, so this slide is actually central. So what is a method? A method is introduced as a function defined inside a class. Its role is to define the behavior of an object. Unlike a standalone function, a method can access object data via self. That means methods are how objects do things using their own internal state. Here the student class now has both a constructor and a greet method. The greet method prints hello along with the self.name. This is a very clear example of behavior using internal data. The object is not just storing information anymore, it is acting on that information. Here you can see the method invocation with s.greet. The dot notation is important because it means we are calling the behavior that belongs to that specific object. The object is not just passed to the method manually. Python uses it as the current instance when the method is called. The output is hello Ali, which confirms that the method successfully used the object stored name. This reinforces the connection between the data and behavior. The name is stored as an attribute, and the method uses it to perform the object's action. Here is to reinforce the idea that methods define what an object can do, attributes describe the object, while methods express its behavior. This is one of the cleanest ways to explain the structure of OOP. Instantiation. So it is a process of creating objects from a class. This slide is describing it as bringing the blueprint to life, which is a very effective way to understand it. A single class can be instantiated many times, producing multiple objects that will all follow the same design. Here we are having two objects, S1 student with the input Ali and S2 student with input Sarah. This is important because it will show you that one class is not tied to one object. The same structure can produce many independent instances, each with its own attribute values. Same class, different objects. So this is to highlight the idea of many instances. The same student blueprint can be used to create many separate students. They all share the same structure and methods, but each object can hold its own specific data. Now let's go to encapsulation. What is encapsulation? So it is introduced here as the idea of bundling data and methods together and protecting internal details from outside access. The goal is not just grouping, but also controlling how data is accessed and modified. This helps prevent misuse and keeps the system more consistent. Why does it matter? So this is just now to explain the motivation of encapsulation. Encapsulation helps protect data, define clear interfaces, and create a kind of security layer between internal state and external code. Instead of allowing anything to modify internal values directly, we encourage interaction through controlled methods. This example is using an account class with self. So the leading underscore is important because it signals that the attribute is intended to be treated as protected. It is a convention that tells other programmers the value should not be freely modified from outside of the class. So self dot underscore balance. So this underscore balance is what shows that it is protected. Underscore in front indicates protected. This is the naming convention. In Python, a single underscore does not make the attribute truly private by force, but it communicates intent. It tells us that the attribute is part of the internal implementation and should be handled carefully. Now we will broaden the view again by seeing the real programs combine many objects and how the main program logic coordinates with the interactions. Objects hold data and behavior locally while the main program manages overall flow. This is how object-oriented design scales beyond one toy example. This example is creating a list containing student Ali and student Sarah, then loops through the list and calls greet on each object. It shows that the objects can be stored in standard data structures and processed like other program values. The output shows hello Ali and then hello Sarah, one after the another. This confirms that each object in the list responds using its own data. The same method is reused, but the result depends on the individual instance. So objects are not isolated. They work together within systems. System logic often comes from the collaboration between multiple objects, each responsible for its own part of the overall behavior. So system is equals a collection of objects. A system can be thought of as a collection of interacting objects. That perspective is useful in modeling as well as other interdisciplinary parts of like engineering because many real systems naturally consist of multiple components with different roles. Now I will introduce class variables as data shared by all objects of the class. So these are defined inside the class but outside methods. The key distinction is that they belong to the class itself, not to any one particular object, so all instances can access the same shared value. The example class student school equals Monash is simple for you and clear. It shows that some information does not need to be stored separately in every instance if it is meant to be common to all students. This is exactly the kind of data class variables are for. Now the contrast is made with instance variables, which are unique to each object. These are typically created inside _init_ and hold object-specific data. For example, one student can have the name Ali and another can have the name Sarah. The data is not shared. Now let's look at shared class versus individual instance. So this is a major distinction in OOP. Class variables are shared while instance variables are individual. You may confuse these two, so it's important to understand that shared values belong to the blueprint while individual values belong to each actual object. Now I'm going to highlight to you one of the most common beginner mistakes, forgetting the self parameter in a method definition. When that happens, Python still passes the instance during the call, which causes a mismatch in the number of expected arguments. The resulting type error is a very common sign of this mistake. I'm going to show you now another common pitfall, forgetting _init_. Without proper initialization, attributes may never set, and later method calls or attribute access can fail. The core message for you is that good initialization is essential to make objects usable and reliable. Here's an example that shows a class with the div greet and no self. This is a useful explicit demonstration of the mistake. It will help you connect the abstract warning from the previous slide to a real code pattern you may accidentally write. So the fix is to add self parameter. The fix is concise but important. Add self. So the instance methods in Python must include self as the first parameter so the current object can be passed in automatically and used inside the method. Now a mini project. So to model a simple system, we first identify requirements, key objects, and interactions. This is an excellent habit for you because OOP is not only about syntax, it is also about deciding what objects exist in the problem space and how they should behave. The mini project defines a room class with attributes name and temperature and a method status that returns hot if the temperature is above 28, otherwise normal. It maps directly to a real entity and demonstrates how behavior can actually depend on stored object state. This creates a room object called room1, and then has the value 30, and then prints r.status. So this is a clean example for you to see how to use an object in practice. First, create it with specific data, then call its method to make a decision based on that data. The output is hot, which makes sense because the temperature passed in was 30. And the status method checks whether the value is greater than 28. This is a mini example of how OOP can model a real-world rule in a simple and reusable way. So this is to summarize the room example nicely. The object corresponds to our real entity, and the method corresponds to behavior or decision-making associated with that entity. This is capturing the sense of OOP very well, that object equals real entity, and method is behavior. Let's return to the key distinction. Classes define structure while objects represent real things created from that structure. The blueprint versus entity framing is repeated here, which is going to be helpful for you because it's a single most important conceptual distinction for this topic. Now I'm going to reframe the topic in terms of competencies, modeling, structuring, and reusability. These are exactly the benefits of OOP that it aims to provide. It helps you see they are not just learning syntax, they are learning a way of designing software systems more effectively. OOP is not just a programming style for its own sake, it is a way of structuring code so it reflects the reality of the system being built. That is why it is especially useful in domains where software must model real entities, components, and interactions. So this is for you to apply OOP by modeling real-world objects in new system. This is a very good way for you to have this practice and also a good way to learn OOP. So identify entities, give them attributes and methods, and build small systems from those objects.